So, reviewing the spring here. What is the work required to stretch a spring with a stiffness K from its natural length to X meters past its natural length? Remember that the force required to stretch a spring, so if it's a normal spring, the force required to stretch it is related to the displacement by constant rate of change, right? By constant rate of change. So that, given any change in the amount you stretch it, the required force to keep it there would be K times that change, right? So this is constant rate of change. And so that's our force. So what would the work be? What would be the work to stretch a spring a distance of K? Carolyn? I think I got to get here at like 9:20. Let's be ready for you guys. Okay, say it again. Integral from 0 to x, right? So this is going to be accumulated work, right? That force increases as you gradually increases the further you stretch it. So we can't just use, force times distance. We have to do integral. So the integral from? And then we want what? The rate of change of work. What's the rate of change of work? Force, right? The rate of change of work is force. So what's the force? Force required to hold the spring at a displacement of x is kx, right? So it'd be k, t, t. Okay? So then I introduced a question like this last time. It takes 50 joules of work to stretch a spring to 0.08 meters past its natural length. How much additional work would it take to stretch it from 0.08 to 0.13? So, can I solve for the constant by doing 50 equals kx and solve for the 50 equals k times 0.08 and get the constant? Does that work? Why not? Because what is 50? It's the work to stretch it there. It's not the force to hold it there. If 50 newtons was the force to hold it there, then that would work fine, and we could solve for k. But this is 50 joules to stretch it, right? So how would I describe what that 50 is, right? 50 is what? It's the work to stretch it. So integral from? Okay. Of? Since this is just a number, I can use x in there, that's fine. Right, the problem is using the same variable here and here. So I have a definite integral, then I can just throw x in there, that's fine. Okay, and so what am I trying to solve for? I'm trying to solve for k. And we said last time, once I solve for k, then getting this work to stretch it from 0.08 to 0.13 would be no problem. But what about this? Solve for k. We said there's a problem here. What's the problem? Remember? How do you solve for k inside of an integral? Who knows, right? This is open form, right? This is open form. So we need something else, right? So the problem here is open form. So if we could get what? If we could have an equivalent closed form of that expression, then we could solve for k all day long, right? So here's a situation where open form, while it's very nice for displaying the process, for showing the behind-the-scenes mechanics of what's going out of accumulation, right? It's showing us exactly like the whole backdrop of accumulation and where it comes from. It's not very helpful in solving this problem, right? So there are benefits to both, right? Closed and open form. So here's a very situation where we really need closed form. Okay, we also saw, what did we see in the, remember when we did the acceleration, and you had it for homework too, the acceleration, speed, displacement. And remember when you try to graph that displacement function, if it's based on the open forms of speed and acceleration, right? It took a long time, right? Even GC, it takes a minute to come up with all those points. Okay, that's because of open form. Closed form, the whole graph just pops on the screen instantaneously. Okay, so we saw that. So we have motivation, right? We have lots of motivation to take these open form, open form accumulation functions and get closed form. So that's what we're going to spend the next couple weeks doing is techniques, algebra techniques to get closed forms from open form. So let's see how that works. Okay, so here let's see how what's gonna be the backdrop here, the background behind getting closed form. What's the net accumulation of a quantity given by function f starting from x equals a? So function f is giving f gives values of the quantity. Okay, f gives values of the quantity. So can you write an expression that gives the net accumulation of that quantity starting from x equals a? Can you write an expression that gives that? Give it a shot. Should be able to. Bless you. Okay, Avi, you're up. Starting from x equals a. Okay, integral from a to x of f of t dt. What do you think? So the integral from a to x of f of t dt. Where is Marcelina? Marcelina here? She's here now. Jeffrey, what do you think? You agree? Yeah. The integral from a to x of f of t dt. Carolyn, you agree? Okay, so you just said f of x?
No, I just put
f dt. David, what do you think? We haven't gotten it yet, so that's why I keep asking people what they think of these answers. Haven't gotten it yet. So what is the accumulation of a quantity where the quantity is function f gives the value of the quantity? David. Okay, is it so? Someone, yeah. Yeah, it's the rate of change of f, guys, right? If the quantity is f, then we need the rate of change of f, right? Not f, right? So if that's net accumulation of the quantity of f, right? Okay, so now I want to write the function f using this expression. So I want to write, what is f of x? F of x equals what using this expression? So this is the net accumulation of quantity f starting from a to x. Now I want to write an expression for f of x. How would I write f of x? Where's Brandon? He made his guest appearance last time. Where's Chris? Christopher.
Would you add f of 0 or f of a plus the a to x?
He wants to add f of a to that. And that'll give us the function f of x. What do you think? That's it, right? That's it. We get all the accumulation from before up till a plus the bit-by-bit accumulation from a to x using the rate function, right? And this is what? This is our total accumulation function. This is our total accumulation function, or amount, right? Amount. So net accumulation is just the integral. Total accumulation, you add all the accumulation from before up to a, and that's the f of a. Okay, so what I'm going to do is I'm going to subtract f of a from both sides. I'm going to get this. So now both sides represent what? Both sides of the equation now represent what thing? What quantity? Net accumulation from a to x of f, right? Of the quantity that's given by f. So now both sides express net exact accumulation or exact amount of change, but in different ways, right? That one as final minus initial, and this one as accumulation of many small bits. So I'll just change the order here, and what do we have? What is that? This is the fundamental theorem, right? The fundamental theorem expresses exact net accumulation in two different ways, as the sum of many bits of change and as final minus initial. Okay, and the fundamental theorem is going to be key to us finding closed form from open form. Okay, so we're going to use the fundamental theorem to write open form accumulation functions, like on the left, in closed form, like on the right. Well, so the right expression, the way you're looking at it now, is still an open form expression when you write f of x minus f of a. But once we have actual examples and actual functions, then that right side will be closed form. Okay. So then the question is, how do we get f, the function f? So we'll have an open form like this over here on the left. And what we need is a closed form, function f, right? Function f. How are we going to get that from what we have over here on the left? How are we going to get function f? So let's ask it the other way first. How do we get the rate of change of f from f? Derivative, right? So this rate of change function is the derivative of f. Therefore, if we start with the open form and we want to get f, we're going to need antiderivative, right? Why? Because we know the rate of change is the derivative of f. Therefore, if we have the rate of change, we need the antiderivative, right? We need the antiderivative. Let me see it again. Here you go. Cool. It's just lacking color, that's all, right? Okay, so this is the key. The key to getting these closed form, and that's what you practice in your homework, the key to getting these closed form accumulation functions is antiderivative and the fundamental theorem. Okay, so here it is, closed form accumulation. Here's our model, right? So I'm going to give you a bunch of expressions, and for each of the expressions, you're going to first explain the meaning of the given expression. Include all the specifics, a full detailed meaning. Okay? Then I want you to write a computable expression or a closed form that gives its value exactly based on what we just said, right? Based on the fundamental theorem and the fact that f is the antiderivative of the rate function, right? So you're going to, part B means write the computable version of the open form using the fundamental theorem and antiderivative, and then solve that. So once you get the closed form, if it can be simplified, you want to simplify it. Okay? So let me have you write down the first three. So write down those three. I'm going to go take attendance. I'm going to get out of the screen. So write down these three. Okay, and just to recap, for each of these three, for each one, you're going to have a person you're talking with, and you're going to practice explaining the meaning of the whole expression, including all the details. Then you're going to use the fundamental theorem and antiderivative to write a closed form. Then you're going to simplify the closed form or solve it if it's appropriate. Okay, whatever. Simplify, whatever there is to do on that first version of the closed form, do it. Is the task clear? Okay. Everyone's working with somebody else, especially on this part A. Okay? So get a partner, talk these out. Okay, see how we did. Kara, you're up. So the first one, can you tell me what it means? What that first expression means? Nice. So it's the net accumulation from negative 1/2 x of some quantity whose rate of change is cosine of x, right? Whose rate of change is cosine of x. All right, and then were you able to start a closed form for that, Kara? But what? So what are we saying? Remember what f is? F is the. How does it relate to our rate function? F is the what? Antiderivative. In other words, and what's an antiderivative? It's the function, what? Whose derivative is the one you're given, right? So it's like what we're thinking. What function, if I took its derivative, would I get cosine u? Sine, right? So we're going to follow this. So my f is sine, so I'm going to have sine of x minus sine of negative half. How many, before I started talking, how many people had that, got that? Good, lots, great, all right? This one can't be simplified, we're done. But look, we got a closed form for this, so this is the open form accumulation function for that accumulation of the quantity with the rate cosine u. So this is the closed form. It gives the exact same values as that. If we graph that one and we graph this one, what would we see? The exact same graph, right? It'd be the exact same graph. For every x, you're going to get the same net accumulation. We graph both of those. Nice, okay. Megan McGrody. Next one. So tell me what the meaning of that expression is. The meaning. So what is the given expression, what does it mean? Net accumulation. Okay, is it the accumulation of 3e to the w? Right, so it's the accumulation of some quantity, right? Some quantity. And what do we know about that quantity? The rate is 3e to the w, right? So it's the quantity that changes at the rate of 3e to the w. It's the net accumulation of that quantity from 0 to x. Okay, now you want to, so what did you have for? So why are you using the exact same function? Because this is the function whose rate of change is the same. It's the one very special function whose rate of change is the same as the value of the function itself. So these exponential functions would be the only one where you would just kind of, you rewrite what you started with, right? Just rewrite what you started with. Okay, and so can we simplify that one? What is it? Notice the minus 3. Notice that we started at 0. Okay, so this is a big problem for students. We started at 0. And did we subtract 0? No. Just because you start at 0 doesn't mean that that second term goes away. Students try to do all the time. They say, oh, 0, right? It starts at 0, so all I need is the first term. But what happened here? You have minus 3. You have to have the minus 3, or it's not the right function. Question?
So do we need like plus C to all of
No.
them?
Mm-mm. Don't worry about plus C. So we've got plus C right here. That's plus C. Minus f of a is plus C. That's what it is. Because these are specific definite integrals, right? So the plus C is like when you're saying, like when you put a here, you're saying it's all possible. It's like the whole family of closed form. But here we have one specific function, so there's no plus C. Okay, very good. Next one. Claire, tell me the meaning of that last integral. Okay, did you say the net accumulation of t to the fourth? Right, of a function whose rate of change is t to the fourth. Right, so it's the net accumulation from 1 to x of some function or quantity whose rate of change is t to the fourth. And were you able to get this one? One over 5, x to the fifth. And so why this 1 over 5 x to the fifth? Remember, we're thinking about what function, if I took the derivative of it, would I get x to the fourth, right? So why do we need the 1/5 x to the fifth? Right, so the power rule for derivative means reduce the exponent by 1, right? So antiderivative, we're going to do what? We're going to raise it by 1. But when you raise it by 1, you get x to the fifth. The derivative of this is 5x to the fourth. A 5 that we don't have here. You see? So how do we change that to make it right? Divide by 5. Put a 1/5 in there, and now we get 5 times 1/5 is 1. X to the fourth. There's our rate function. Okay, so this is same as 1/5 x to the fifth minus a fifth. So look at this, we're already doing it. We haven't even done a whole class yet. We're already writing closed forms for easy rate functions, right? For easy ones. So these are easy rate functions where we think, okay, back from Calc 1, what function had that as its derivative, right? So you have to be really good at your derivatives, so good that you can kind of do them backwards. You're thinking, what function, if I took the derivative of it, would I get my rate function? That's your antiderivative. Any questions on these? Good on these? All right, well, then do something harder. Again, you have to have this mindset. What function, if I took the derivative of it, would I get that? So now you have to think about some of the harder derivatives that you did back in Calc 1. Think back to the harder derivatives you did in Calc 1. You say, what function, if I took the derivative of it, would I get that? Or what derivative rule does this look like it's the result of, right? Remember your derivative rules? Product, chain, quotient rule. Jeffrey, any idea? Looks like the chain rule. Kinsey agrees. So if it's the chain rule, how do we undo it? Remember the chain rule, you took the derivative, and then what? You multiplied by the derivative of the interior function. Do you remember that? That's the first technique we're going to work on Friday. We'll start a little bit today. But this is this idea of undoing the chain rule. You have a derivative that's from the chain rule, and we've got to undo it, go backwards. So were you able to do that, Jeffrey? It's going to be gone, right? Because when you took the derivative, that popped out of here, right? So when you go backwards, the 2a will be gone. You hear that? That's good, all right? So what we have, this is really what? A squared plus 3 to the half. So now, what function gives us a derivative like that? A squared plus 3 to the half. Nice. So we're going to do a squared plus 3 to the... We're going to raise the power by 1, right? The power rule. But then, thinking about taking the derivative of that, we'd have a 3/2 that we don't have over there. You see that? If we took the derivative of this, we'd have 3/2 times this to the 1/2. We don't have the 3/2, so 2/3. What about the 2a? Is it right? Yeah, because of the chain rule, we're gonna multiply by the derivative of the interior function 2a, and there's the 2a. So here's the thing with these. If you're not sure, you can still take a stab at it, and then what can you do? Find the derivative and compare it, right? This is gonna be my song and dance, right? Don't feel like it has to be perfect on the first thing. Just give it your best shot. Then take the derivative of your result and compare it to your rate function. If it's exactly the same, then your attempt was correct. So let's do the derivative, right? So the derivative is what? 3/2 times 2/3 times a squared plus 3 to the 1/2 times 2a. That goes away, and we're left with this. Is it exactly what we started with? Yes, it's exactly what we started with. Therefore, that attempt at the antiderivative is correct. So now we want to finish writing out the closed form. Jeffrey, you want to finish it? Oh yeah, so that'd be, that's right. That would be x. Okay. Is it right? Nailed it, right? That's it. So it's going to be f of x minus f of 10, which would be, we get 103 to the 2/3, 103 to the 3/2. All right, so let's actually do this one. Let's actually graph this and see if we get the same thing, right? So here's another way you can check, right? So you can check your antiderivative by taking the derivative. You can check your whole closed form by graphing both in GC. Which one do we, so before we do that, which one do we trust? If we were to graph both of these, which one would we trust? Left side or right side? Left, because we didn't do any algebra, right? Algebra is all this opportunity to mess up, right? All this opportunity to make mistakes. We trust the open form. And so then if our closed form is the same, then we know we did it right. So I can just do y equals 0 to, or is it 10 to x? I have no idea if this is going to be, how this is going to look, but we'll try it. So 2a squared plus 3. So I'm just for time's sake, I'm bypassing writing them each as functions and then graphing the functions. So this will work just fine. Yes, x. Thank you. How does the top one look? Did I do it right? Did I type it in right? How do they both look? Correct? Okay. Let's see here. Something's not happy. Okay, and if we zoom out, hopefully we're going to see something. Let's do red and blue. Okay. I just need to I'm going to turn the first one off, turn the first one off, all red. Turn the second one off, all blue. So we got it right. So that we've got a closed form. That second one now is a closed form for the first one in open form. Okay, got another one for you. There we go. Lower right corner. Go. So k is a constant, like 4 or 10, right? So it's just a number. Okay, Adriana. Can you get me started on this? No? Kyle? Anything? Okay. So what happens? What's going to happen to the k? We're just going to hold on to it, right? So we're just going to hold on to the k. So the antiderivative is just, we're at the antiderivative first. Antiderivative. We're going to hold on to the k. And then you said? Half x squared. So if you're not sure, what can you do? Take the derivative. Take the derivative, right? Derivative is 2 times a half. 2 times k times a half is k times x to the first. Is that what we have? Perfect. Got it. So now we're going to accumulate from 0 to 0.08. So what will this be as we accumulate from 0 to 0.8? We've got our antiderivative. What should I write? Harrison. Good. Which equals? Okay, here's a case where 0 gives you 0, right? So yes, sometimes you plug in 0. Sometimes you plug in 0 and you get 0, but not always. Okay? So quickly, so what do you recognize this now? What was this? That was the work, right? To pull the screen, to stretch the screen 0.08. And what was the work? It was 50 joules, right? 50 equals 1/2 k times 0.08 squared. Can you solve for k? Piece of cake, right? Piece of cake. We can get k, and then we can figure out for that spring, we've got k now. We can figure out the work for any displacement. We can figure out how much work we have the k. Okay, please give your attention to our friends here from the Navy?
Yes.
Navy,
Sir.
okay.
All right, thank you, sir. Appreciate the time. Be really quick. I got your rooms mixed up, sir, so I barged in the wrong classroom, so be quick. My name is Lieutenant Paul Heff. This is Lieutenant Kevin Nui.
Nuclear power on submarines. That's cool. That's cool. All right. So let's do it. Let's finish the problem. What do we got? So what is k? 100 divided by 0.08 squared. It's going to be a big number. So let's use GC to do this. Going back to the problem, here it is. All right, first of all, value of k is, what did we say? 100 divided by 0.08 quantity squared. So what is K? K is that. All right, 15,625. And then we wanted the work to stretch it to 0.15, to 0.13. So now how much additional work would it take to stretch it from 0.08 to 0.13? If now we know K, K is 15,625. So write an expression that will give the amount of work. Sorry. What do you have? What was it? Anyone write down 15,625? Okay, so if we want to, so now this is the closed rate. This is the closed form version of how much work it would take to stretch it from 0 to x, right? That's how much work it would take it to stretch from 0 to x. And then we could write another integral. So what expression can we write? That's the, so I want to know how much work to stretch it from 0.08 to 0.13. Evelyn, did you get it? What's that? Okay, so if I put 0.08 in for x, then that would be how much work to stretch it from 0 to 0.08. So now I want to get from 0.08 to 0.13. Jesus? Right? And what am I going to put in there? T, I need the t in there, right? I need the rate function, right? Not just k, but the rate function is k times x. Yeah, it doesn't matter. So I need that t in there. So 82 additional joules of work to stretch it from 0.08 to 0.13, made possible by knowing the value of k, which was made possible by having closed form, right? Closed form enables us to get the value of k, and then I can get the actual work that was asked for.